Welcome back, and I do hope as ever you and your family are keeping well. So what we're going to do in this lesson is a bit of a roundup of the electricity topic, and I'm going to look at every single formula that you have to deal with, and we're going to do an example of each one so you've got a good understanding of the sort of maths that might come up at GCSE. So there's quite a lot of these, as you know, and quite a lot of them are given to you on a formula sheet anyway, but you have to know what the formula mean and when to use them. So we're going to kick off with resistance. So resistance. So you'll remember that resistance tells you how badly something conducts electricity. So you put a potential difference, an electrical pressure in volts across it, and you see how much flow you get through it, how many amps. So I'm going to use the same little circuit again and again, and bear with me, but I'd like to draw the circuit in front of you so you remember how these things work. So we've got our power supply here. You might call it a battery, but that's really a cell. We've got positive, negative. We're going to measure the current flow in the circuit with an ammeter in series. We're going to go through the thing that takes energy from the electricity, so that's the fixed resistor, and come back to the power supply, the battery. I'll call it a battery, I know it's a cell. So we've got a flow of electricity this way, and that's caused by a potential difference, a pressure from the power supply. Now, if you think about it, an ammeter, if you remember, is just a wire. Okay, it's a measuring wire, but it's a wire nonetheless. So if I connect a voltmeter between here and here, okay, that point there is the same as this one, and that point there, because the ammeter is just a wire, or behaves like a wire, is the same as that point. So in this case, the potential difference across the battery measured there is the same as the potential difference across the fixed resistor. Right, so we've set up the sort of circuit we're going to use. I'm going to put a current here of 2 amps, so I'm making up that number. This has got a resistance, and we're going to measure the voltage from the battery, and I'm going to say that that's like we get at school from our battery packs. So that's 6 volts. Now, you'll notice a couple of other things, that the current coming from the battery goes through the resistor and dumps energy as heat. Okay, it does work. It gives heat out of the resistor. Now, resistors really have 2 purposes. One is to make sure the amps aren't too large, or imagine the resistors in a toaster or in a hairdryer. They're designed to get hot. They're designed to give out lots of energy from the power supply. But remember that conventionally current goes from plus to minus. So I'd like you to think of energy being brought to the resistor, released by the resistor, and then the charge going back to the battery to get more energy. Now, there's some confusion historically about which way electricity flows, so I'm going to stick with this direction. But we do know it's electrons that flow in the circuit, okay? But the important thing is you can't lose or gain electrons, they're in the material. So just imagine, I'll call it charge now, as coming from the battery with energy and then going back to get some more. So the current there, 2 amps, must be the same as the current here, okay? So what we're going to do now is very quickly work out what is the resistance of our fixed resistor. So, a bit of an introduction there, and I won't need to do that again now. You understand the circuit we're going to use. So, let's work out the resistance of the fixed resistor. Now, the formula for this can come in a number of different forms. I'll start off with the way that it's often given in textbooks, and that is V equals IR. So you have to get your head around what all these letters mean. So let's just indicate what they are. So we know that this is the potential difference measured in volts. Okay, the kind of electrical pressure of the battery, desperately trying to push electrons, push charge around the circuit. If it's trying to push through a material, that material has resistance. Okay, so we know that this is the resistance, and it must be measured in ohms. So at GCSE, watch out for kilo ohms. And finally, this rather annoying letter I, okay, is the flow, the current. And we know the current is measured in amps. Okay, so the trouble with this is sometimes getting your head around all these letters. So let me just remind you what we've got here. We've got a name, current, we've got a unit, amps, and we've got a letter that abbreviates the name. I always say to pupils, think about that as the intensity of the current flow. Okay, now one thing you have to be able to do at GCSE is rearrange formula. So if V equals IR, divide this side by I. So R is V over I. Okay, so let's do our little example. So this one above. So here, in the example we've got, and it's quite an easy one. Yep. R equals V over I. So R equals V. The potential difference is 6 volts. The current is 2 amps. So that gives a resistance of 3. And there's our unit, ohms, or OHMS. Okay, so lots of formula to deal with, but we've got the first one out of the way. Okay, and you might want to look up Ohm's law that kind of goes with this formula, but put in your head V equals IR. So now we know about resistors, let's look at the formula for putting resistors in series. So if you remember, that's putting the resistors end on end. And in a series circuit, it doesn't matter which way round the components go. In other words, you can have the first resistor that I've drawn here, or you can swap them round. It doesn't make any difference. Now, get used to the fact that the battery's up here, and then there's an ammeter down here, and then along we go and back up to the circuit. So I'm just drawing the bottom part of the circuit. Okay, so we know we've got some current flowing this way and coming out the other side, and I'll give that the letter I. Okay, but we are asking ourselves, what's the total resistance? So here's a fixed resistor, the first one, R1. Here's another resistor, R2, and I'm not sure you'd ever get more than 2 at GCSE. And let's give this a value 3 ohms. So that's going to be tough for electricity to go through. The battery's going to have to press to get amps through that. But we're now going to make it even harder for the electricity to ever get through the circuit. It's not only got to get through the 3 ohm, but it's also got to get through a 7 ohm resistor that I've decided to put there. And if I swap it round, it makes no difference. The battery doesn't really know that there are 2 resistors there. It just feels that it has to push through this much bad material, this much resistive material. Okay, so the formula is obvious, I think. Okay, so the resistance in total. Okay, so I'm using this little subscript here just to remind you which resistance it is. Okay, the resistance in total is just add them, okay, in any order. So let's add R1 to R2. Okay, best to do that in ohms. Yep, so what we've got here is we've got R total is equal to 3 ohms plus 7 ohms. You don't need to put the ohms in there, obviously, because we're just doing the maths. So the total resistance, should we call it RT? The total resistance is 10, and now we must put the units on. And they might ask at GCSE, OHMS or ohms. Okay, so to do resistors in series, just add the values that they give you. So now for the one that we don't really do mathematically at GCSE, but they can still ask you questions about it. What happens if you have resistors in parallel? So I'll go back to the circuit that we had. So there's our power supply, our batteries or cells. We're going to have a resistor here, and we'll go back to the battery. Okay. So let's look carefully at this, and if you're thinking this is a bit simple, just bear with me. Okay, this resistor here, we'll call it R1, okay, is going to draw current. There's going to be amps flowing through that, okay. Notice that the voltage across it is the voltage of the battery. Now, it's this next stage that's the tricky bit, okay. What happens if we add another resistor here? And I'm going to draw it as a dotted line to make it perfectly clear that it's nothing to do with this bit of the circuit. Okay, so have a look at this resistor we've added here. Let's call it R2, the second resistor. Okay, look at where it's connected to. It's connected to the battery. So this resistor here, R1, doesn't really know about this one's existence. This one is just connected to the battery as well. And here's the clever bit, okay? If we get some amps flowing this way, some current, yeah, let's call that I1, the current through that one, okay? The battery is going to feel a resistance. But here's the clever bit. If we add another resistor, electricity will flow this way as well. So the battery has to provide current for this resistor and R2. So we're going to get some current going this way into this one, I2. Now, if you look at it, we've got the current we had before, plus this extra current to kind of give energy to this resistor. So mathematically, the current coming in will be I1 plus I2. But the point I'm trying to make is more amps. Yeah, if we don't have that resistor, just I1. If we have this resistor, we've got to feed current to this one and this one. More amps, yeah, more flow means less resistance. Okay, so as we put more and more resistors in parallel, the current goes up and the total resistance goes down. So I'll give these a value. Let's make this one 10 ohms. And let's, for the sake of it, make this one 25 ohms. Okay. So just have a look at that circuit and think, okay, 10 ohms will have some current through it. 25 ohms will have some current through it as well, but not as much, okay, just under half. But it still draws current that wouldn't be taken before, okay. So the total resistance of the circuit has gone down from the 10 we put in, okay. So the total resistance, R total, yeah, is always lower than the lowest resistor. Okay, so find the lowest resistor and go, that takes amps. Realise the next one will take more amps, or when I say more, extra amps. Okay, so the resistance in total must have gone down. So I look at that circuit and straight away I go, it's not 10 ohms because there's more current than we thought, so it must be slightly less than 10 ohms. Tricky, isn't it, when we've added a higher resistance here? Okay. Something else to note that I mentioned, that the total current, should we have it coming down here? This is getting a bit A-level-y now. The total current, yeah, I total, will be equal to the current through the first resistor plus the current through the second resistor. And the most important thing of all with parallel circuits, okay, that the voltage, so the or potential difference we should really call it, the voltage, I'll call that PD, potential difference, across each resistor is the same. That's not true of a series circuit, yeah? The battery is between here and here, so this one gets some of the voltage, potential difference, and this gets the rest. Whereas here, remember, this resistor is directly connected to the battery. This resistor is directly connected to the battery and therefore draws more amps and it's going to flatten the battery quicker. Okay, so now let's look at the charge that flows in a circuit. Okay, so a quick revision of that. If you remember, charge is a bit like the electrons, I suppose, in this case. It's what carries the energy around the circuit. So if we switch it off, no charge will be moving, no charge will be flowing. But if we switch it on, charge will be moving around the circuit. Okay, it's basically the current flow tells us something about the charge flowing. Okay, and you need to be able to calculate how much charge flows through something in a circuit if you switch it on for a certain amount of time. Okay, so the first thing I'd like to remind you about is what amps are. So I, which is the current. This is an important idea in physics, okay, measured in amps. It's the amount of charge flowing per second in a circuit. Okay, the amount of charge flowing per second. Now, it's a bit tricky this. Do you remember what charge is measured in? Charge is measured in coulombs. So it is the number of coulombs flowing per second. It might be helpful to sort of remember that little bit, and we'll deal with that in a second. Okay, so what we need to be able to do is to work out how much charge flows through a place in the circuit in total if we leave it on for, say, 2 minutes or something. Okay, so let's have a look now at it's a bit of a sort of question. Let's have a look at the total charge flowing that's flowed after a period of time. Through a point. And we'll call that point P on the circuit, okay? So imagine this little point here. Let's call that point P, okay? So we've got a little point P there, and we want to calculate how much charge has flowed through that point after a certain amount of time, okay? So we need a formula for this, and more letters, unfortunately. And the formula is Q, the total charge, okay? Don't you want to give that the letter C? No, Q, the quantity of charge, is equal to, now I think this is going to be sort of obvious really, how much charge flows every second. But if you leave it on for more seconds, then you'll get more charge. So multiply by how long you leave that charge flowing for. Okay, so we'll just label all these letters. So this is the charge, and it's measured in coulombs. Yet again, really confusingly, you can use the unit coulombs, and you can use a big capital C for that at the end of an answer, like 6, big capital C, 6 coulombs. Okay, you know that this is the current, and I can just abbreviate that to amps, and this is the time that the circuit's on for, and it's in seconds. Okay, it's not in minutes. Okay, so let's do a quick question. So let's have the circuit that we're looking at all the time, so you don't need to memorize different circuits. Let's leave this on for 2 minutes. Okay, so immediately you go 2 minutes. No, that's 120 seconds. We should be working in seconds. Okay, so how much charge has flowed around this circuit or through that point or through the resistor or through the battery in 2 minutes? Okay, so we've got our formula, Q equals IT, so Q equals IT. So the amount of charge that has flowed in this time is how many amps? We've got 2 amps times by the time in seconds, 120. Okay, so you don't need to reach for a calculator for this one. So the charge that has flowed will be 240 coulombs. I'll write that underneath. Okay, I'll put it in brackets. So that's another formula that you need to be able to use at GCSE, and now you know how to calculate the amount of charge that's flown in a circuit in a certain amount of time. So now let's look at power in electrical circuits. And this is a little bit fiddly, so it's going to take a bit of explaining. So the first thing you need to know is what we mean by power. Okay, so power is the amount of energy given out or transferred per second. So power is measured in joules per second. So if you think about it, the battery is going to give energy to this resistor, and the resistor is going to get hot, and it's going to dissipate, give out that energy as heat, and a certain number of joules per second. So we can write that as joules per second. Okay, but lucky man, he got to be named. He got his name taken to represent joules per second. Mr. Watt of steam engine fame. Okay, so we can say that a joule per second is a watt. Now you might be wondering what's going on here. It's just you can say 6 joules per second, or you can say 6 watts. You know, so a light bulb could be 100 watts, which is the same as giving out 100 joules per second. So the formula for power in electric circuits: how much energy does something give out per second? Well, if we turn the current off, it won't give out any energy. So it depends upon the current. More current, more power. If we turn the battery off, the circuit won't work. So more volts, more potential difference, more power. So that's how you remember it. Okay? The power in any electrical circuit is just the volts times by the amps, or more correctly, the potential difference times the current. Okay. Now, there's something I'm going to do here which you don't really need to know, but it's quite interesting, and it shows you how from volts and amps we get joules per second. Because when you look at that, that's a volt amp. Volt amps is joules per second. Yeah, it is. If you remember that power is measured in joules per second, okay, voltage, and this is a bit advanced to be honest with you, it's a little bit A-level-y, voltage tells you how many joules on each coulomb of charge that flows. And current, that we're timesing by here, tells us how many coulombs flow in the circuit per second. So if you have a look at that, it's quite neat, isn't it? You can see that by multiplying volts and amps, potential difference in current, we actually get joules per second. I don't think you'll be asked to do that at GCSE, but I wanted to show you that. So let's calculate on our circuit above what the power is. So here, this circuit, the same one we're demonstrating with every time. The power will be equal to VI, or a lot of textbooks write it as IV. They put them in alphabetical order, which is totally okay. Yep. So we've got the power is 6 volts times by 2 amps. So the power is 12 joules per second, or if you prefer, you can write the power is 12 watts. So there's another little formula, and it allows you to calculate the power in an electric circuit. But there's something else I need to tell you, and we need to take this just a little bit further for the higher marks at GCSE. Okay, so there is another way we can calculate power. So if you remember from the formula above, so if you know these two things, that power is equal to VI, okay, and you remember the other formula that we dealt with earlier on for what V is, V equals IR, okay. Then you can do something a little bit clever. So follow me through on this. Okay, P equals VI. P equals V, which is IR, V, yeah, V, IR, so that V there, multiplied by I. So what I'll do, if it isn't clear, is I'll sort of do this, that is the IR. Yep. And then you can see that if you do that, therefore, P, the power in a circuit, is IIR. I squared R. Okay. Now, you might wonder, gosh, what are scientists doing here? Okay. This is an incredibly useful formula. It tells us lots of things about how power is affected by current in circuits, but it also allows us to calculate the power directly if we only know the current and the resistance. Okay, so this is a formula you need to be familiar with. So power in an electrical circuit can also be I squared R. So one or two of you might be wondering, well, we've got that formula and we've got this one. Which one gives the right answer? No, they both give power. So let me prove to you that it works in exactly the same way. Okay, so in this above circuit, we're going to do P equals I squared R. So we've got P equals 2, that's the amps, squared, times by the resistance 3. Okay, so the power will be 4 times 3, and look at that, the power is 12 joules per second, or if you prefer, 12 watts. So P equals I squared R gives exactly the same answer, and of course it should, because things in physics are consistent. Yeah, both give 12, so that's fine. I just want to make one more point, because it will come up in some of the work we'll do. The power that's delivered to a circuit, or the power that's given off by the resistor, so that could be the heat per second, doesn't depend just on the amps flowing. It depends on the amps flowing squared. Okay, it's a really difficult concept for students, this. So it means that if you double the amps, you don't double the power, double squared. You 4 times the power. Okay, and if you have 3 times the current flowing, 3 squared is 9, you'll have 9 times the heating effect. Okay, so changing currents, increasing currents has a large effect on the power. I don't want to go off onto some different physics for any detail, but power lines, those big power lines on the pylons, you might know or remember, we want to keep the current low in those, because if we have a high current in the cables and a resistance of the cable, then because the current squared affects the power, those cables will get warm and they'll waste masses of energy. So to not waste a lot of energy, to not have a high power, it's better to keep this one lower than it is to keep that one, because you get the squared effect there. Okay, so a bit of a tricky one for GCSE, but importantly so. It used to only be in an A level. So the power that a circuit transfers to a load, something here, okay, is just equal to the current that's provided squared multiplied by the resistance of the load that you connect to it. Okay, so we're almost there. We've got sort of 2 little formula left to do, and they're all about how much energy is transferred in an electrical circuit in total. So we did power, how much is given out per second. So now we need to work out how much energy is given out over a period of time. So to do this, we remember that power measured in joules per second, so power is energy per unit time. So the power is in joules per second. But if I rearrange that, okay, for the energy that would be given out by a circuit if we leave it on for a period of time, E is P times by T. Okay, so the energy given out by any electrical circuit will be the power of that circuit, which you can calculate in with the formula we looked at earlier, multiplied by how long you leave it on for. Okay, so just to remind you, of course, so it makes it really clear, that's in joules, because it's energy. This is in joules per second, and this one is in seconds. So you can sort of see that if you times power by time, you get energy. Okay, so let's have a look at this circuit above. So let's leave this circuit on for 2 minutes. Okay, so it's the same circuit we've been dealing with all the time. Let's leave it on for 2 minutes, and immediately alarm bells are ringing. It's not 2 minutes, of course. Yeah, it's 120 seconds. Okay, so let's work out how much energy this circuit will give out in total. In other words, how much energy will it take from the battery and put into the resistor as heat, okay, if we leave it on for 120 seconds. Just before I do the calculation, some of you might say, so what? It's slightly different with mains electricity, but kind of, this is what you're paying for, yeah? You're paying for the energy. This will tell you how quickly your battery flattens as well, so it's quite important. So, let's see how you calculate this. Well, you've got the formula now. So, the energy released is the power times by the time. So, it depends upon time. Okay. So, we also know, by the way, it's worth pointing out that power, if you remember, this one here, is volts times amps, or more correctly, potential difference times current. Okay, so don't forget that that is VI if you need to calculate the power in the circuit first. And that's going to help us because we only have values of V and I here, so we will need to calculate the power first. So let's do the calculation then. So the energy that this circuit will release is the power, which is volts times amps, potential difference, 6 times current, 2, times by the time we leave it on for, so times by 120 seconds, yeah? So we've got the energy is, that you might remember, it was 12 watts, 12 joules per second, times 120. So if we leave the circuit on for 120 seconds for 2 minutes, it's going to give out as heat 1,440 joules of energy. So that's in total. Okay, so bit more of a difficult calculation there, but I like this bit here where we're using knowledge we had before to work out the power. Okay, now I just wanted to point out one thing about this. Energy transfer in physics, okay, is called work done. So this is the work done, yeah? This is the work done. By the battery, okay? And the battery is actually putting that energy onto the charge that flows round, so it's the charge that does the work here. So this is the work done by the flowing charge. Okay, And at GCSE, they're quite keen that you understand that work goes into a sort of system. So, for example, it could be something like a motor, okay, an electric motor, and that electric motor will convert electrical energy to kinetic. And if you remember, there's not a proper Sankey diagram, to some waste as well, some heat, and a tiny bit of sound. So you can see we can calculate the work done by the circuit, the amount of energy that it's transferred, and it's good at GCSE that you understand that energy, electrical energy, will turn into other forms, and in the case of a motor, it will turn into kinetic as useful and heat as the wasted energy. So now you'll be pleased to hear the last one, and the second method of calculating how much energy is transferred by an electrical circuit. So what I'm going to do is I'm going to just write the formula down. Okay, so the formula is the amount of energy transferred is equal to the charge that has flowed in that time, okay, Q, multiplied by the potential difference of the bit you're looking at. So in this case, it's going to be 6 volts across the resistor. It's the potential difference across the item you're looking at. Okay, so we've only got one thing in this circuit. So E equals QV. Okay, so let's pull this apart a little bit more. Energy is measured in joules. Okay, charge is measured in coulombs, and voltage, you might remember, though it's not really needed for GCSE, is measured in joules per coulomb. So look, there you go. It's consistent that the energy is measured in joules. But I want you to remember back to a previous formula, okay, to be able to do a calculation on this circuit. Do you remember that Q is also equal to IT? Okay, so the amount of charge that's flowed in a circuit in a certain time is the current times by the time it was on for. Okay, well, we had our circuit, so this circuit here was on for 2 minutes, but we remember that is 120 seconds. So let's see if we can use this formula now to calculate the amount of charge that flowed, and then work out the energy that was transferred, the work that was done. Okay, so we've got E equals QV. Yeah. We can then remember that in our case, E is equal to, well, Q was IT, so IT, and then V. And again, I'll just draw in here to remind you that Q is the IT. So let's now put some numbers into this. So the energy that will be transferred will be the current, which is 2 amps, times by the time, which is 120 seconds, times by the voltage, which is 6 volts. And if you bash that out on your calculator or do it in your head, you won't be surprised that you get the same answer as we did in the previous bit, 1,440 joules of energy transferred by the battery at this time. So it's a bit of a circular argument, but there are 2 formulas for calculating the total energy transferred, and this is the second one. So that's it, and well done. That was not an easy lesson to follow with all of those formula to have a look at. I hope you found that really useful, if not interesting as well. Just remember that you are given a formula sheet at GCSE, so have a good look at that. And I'm always interested to comment to students who just go and learn the formula. Okay, that might help you a bit, obviously, learning the ones that aren't on the formula sheet. But rather than slave away learning formula, you've got to be able to use them. Okay, so the purpose of this lesson was to show you the formula that you have to deal with, but you need to understand what all these funny letters mean and how to use the formula in calculations, and it's then you'll start to get the marks. Anyway, I wish you the very best with the electrical topic in your GCSE, and thank you for watching.